So in the previous class, we have discussed about the Schrodinger equation and related concepts, which was in quantum mechanics block 1. Today we shall discuss block 2. Am I audible? Am I audible?
Yes, sir.
So in this block 2, you have some applications of quantum mechanics. These includes simple one-dimensional potential, uh, potential barrier, tunneling, potential wall, spherical symmetric potential, hydrogen atom, so on and so forth. So let us discuss all this. So let us discuss a bound state problem in an arbitrary potential. In order to gain some insight into the method of approach of quantum mechanics, as well as some of the interesting predictions of the theory, we now turn to find out the eigenfunction and eigenvalues of some illustrative one-dimensional problems. And in these examples, the potentials and wave functions vary only in one direction, which you choose to be x direction. So the time-dependent Schrodinger equation, you know, is IH cross del psi by del t minus h cross square by twice m del square psi by del x square plus u psi, where u is the potential. So the corresponding time-independent Schrodinger equation can be written as minus h cross square by twice m del square psi by del x square plus u psi, which is equal to E psi, where E is the energy operator. So you can write d square psi by dx square plus 2I m by h cross square multiplied by E minus u psi is equal to 0. You can see this is a second order differential equation, and its solution depends on the form of potential, that is u, which is a function of x only. And the complete solution can be obtained only if the boundary conditions satisfied by psi are known. So what are the boundary conditions? There are two classes of wave function. One that represent wave packet that are well localized and for which the normalization integral converges. And second is traveling harmonic wave represented by the function e to the power I k dot r minus omega t, in which case normalization integral diverges. So the wave function belonging to the first class, where there is a convergence of the wave function, this represents particles which, if free, are initially localized to a particular region of space by external forces derived from U. And this describes bound states. This describes bound state. So where the wave function converges, it describes a bound state in a particular condition. And the wave function belonging to the latter class, where the normalization integral diverges, the particles which are not localized, they travel through the region under consideration from one distant part of space to another. These wave functions are useful in describing the scattering of particles by field of force. So in bound state, you have your real-time situations where there is particle in a box or in a harmonic oscillator or a hydrogen atom. And in the latter case, where the normalization integral diverges, there you have a free space, and it is very much useful in describing the scattering of particles. Your psi, where x is plus minus infinite, is equal to 0. Then continuity condition. Equation 3.2, which I have discussed earlier, that is your d square psi by dx square plus twice m by h cross square e minus u psi is equal to 0. This can be written in the form psi double dash plus twice m by h cross square e minus u psi is equal to 0. And this is a second order linear differential equation. You know, it has two linearly independent solutions for any energy capital U. So if U is finite everywhere, whether or not it is continuous, a knowledge of the wave function and its derivative along the surface makes it possible to integrate the equation. And this helps in finding the wave function at any point. And the probability of existence of a particle cannot be spatially discontinuous, therefore. So your psi must be continuous across the boundary where U changes abruptly, and you have to further specify the boundary condition on the first derivative of psi. For the purpose, we consider a very small region of space del x localized at the boundary. So the change in psi dash, which is equal to d psi by dx over this region, is given approximately as del psi dash is equal to d psi dash by dx multiplied by del x is equal to psi double dash del x, which is nothing but twice m by h cross square u minus e psi. So for a given particle, twice m by h cross square is a constant. M is the m represents mass, h cross represents h by 2 pi, which is a constant. So twice m by h cross square is a constant, and u as well as e have finite values, and psi is also finite. So your del psi dash tends to 0 when del x tends to 0. So your psi dash is constant as long as u is not infinite. Then we say that psi dash is continuous across the boundary. So we can summarize all these things, and we can say that the wave function psi is finite, continuous, and single valued, and the first derivative of psi, that is psi dash, is finite, continuous, and single valued at all points where u is finite. These requirements also have the consequence that the position probability density for a physical system is finite and continuous everywhere. So what are the general features of this solution of a one-dimensional problem? So the study of one-dimensional problem is significant because of two reasons. First, many real problems encountered in atomic, molecular, nuclear, as well as solid-state physics, which are three-dimensional, can be reduced to equivalent one-dimensional problem. Second, various aspects of bound states and free states of a system can be understood easily from the study of the one-dimensional problems. And your exact analytical solution of the one-dimensional time-independent Schrodinger equation can be obtained only for a limited types of potential U. So before going to specific examples, we consider some qualitative features of the solution of Schrodinger equation in a general one-dimensional problem. Potential. The time-independent Schrodinger equation for a particle of mass m and energy E moving in a one-dimensional potential U, which is a function of x, can be written as d square psi by dx square plus twice m by h cross square E minus u psi is equal to 0. And d square psi by dx square is equal to twice m by h cross square u minus e multiplied by psi. And the nature of the solution is dependent on the relative value of E and U, because your E minus U term will decide whether the nature of the solution. So there is two cases. First, U is greater than E, U is smaller than. So if you look, if u is greater than e, then the right hand side will be negative. And if u is smaller than e, then the right hand side will be if u is greater than e, then the right hand side will be positive, and if u is smaller than e, then the right hand side will be negative. So if u is greater than e, the RHS is positive. So d square by dx square has the same sign as that of psi. D square psi by dx square is equal to some positive value multiplied by psi. So the sign in both sides will be same. Left side it is positive, right side it is positive. This implies that psi is convex to x-axis and is away from x-axis. On the other hand, if u is smaller than e, then u minus e is negative. So your d square psi by dx square, left hand side is positive and the right hand side the coefficient of psi is negative. So it is concave and towards the x-axis, and this can be shown in the figure 3.1 and 3.2. Okay. So depending on the relative values of e and u, the solution psi may be convex in one region and concave in another region. In some cases, if in some region the left hand side, the value of left hand side will be the same as that of the value of right hand side, in that region that will be convex. In some other region, if the right hand side becomes negative, then it will be concave. So this is also shown in the screen. But the boundary conditions demand that the wave function be continuous and be continuously differentiable. That is, the first derivative is continuous. So the general solution is a continuous curve satisfying the boundary condition. So what are the general features of a one-dimensional motion? These features will be illustrated with specific examples. Suppose E is smaller than U. What is the nature of the solution? So if E is smaller than U, then they diverge as x tends to plus minus infinite. Such a solution is not admissible if E is smaller than U everywhere. However, if E is smaller than U in some region and E is greater than U in some other region, then these solutions can be connected continuously. And if E is greater than U and E is smaller than 0, E is negative, then the solution is shown as the second 3.2. So what will happen? This corresponds to a boundary. This corresponds to a bound state with negative energy. The classical motion is periodic, and the energy and wave vector are constrained to have some specific allowed values. There exists at least one bound state. The spectrum of bound states is discrete. The energy eigenvalues are non-negative and non-degenerate. If multiple bound states occur, they are alternatively symmetric and antisymmetric with increasing energy. Okay, so these are the general features of one-dimensional problem. Let us have some specific example. A finite potential well in bound state. So here you can please refer the figure. It is 0 when modulus of x is greater than a, and it is minus u0 when minus a is smaller than x is smaller than a, and your u0 you take it positive. So there are three regions, 1, 2 and 3. In 1 u is 0, in 3 u is 0, and in region 2 u is minus u0 where u0 is positive. So this type of potential has sharp discontinuities at x is equal to plus minus a, where the transition between region 1 and 2 and 2 and 3. Here there is sharp discontinuity and cannot correspond to real physical situation, but it can provide a very useful idealization of many real situations encountered in atomic and nuclear physics. So let us have the solution. So before that, let us have the Hamiltonian. So h cap, which is the Hamiltonian, can be written as px cap square by twice m plus u. So acting on the configuration space wave function psi, h cap takes the forms h cap is equal to minus h cross square by twice m d square by dx square plus u. So here u, which is a function of minus x, that is the potential ux, is a symmetric function of x. So you can write h cap of minus x is equal to h cap x. And the Hamiltonian h cap is a symmetric function of x. And what is the Schrodinger equation? the Schrodinger equation is h cap psi is equal to e cap psi, and you can write it as psi dash plus twice m by h cross square e minus u psi is equal to 0, and it is a bound state, so e is smaller than 0, and you can write e is equal to minus epsilon, where epsilon is positive. So now the Schrodinger equation can be written as psi double dash minus twice m by h cross square epsilon minus u psi is equal to 0. So you now distinguish three different regions, 1, 2, and 3. And in 1 and 3, u is 0, and in 2, u is equal to minus u0, where u0 is equal to positive. So similarly, the wave functions can also be written as psi 1, psi 2, and psi 3 for these three regions respectively. Then solution in the region I, where x is smaller than minus a, and triple I, region 3, x is greater than a. So in this region, u is equal to 0, as I have told you earlier. So your psi 1 double dash minus k square psi 1 is equal to 0. Then your psi 3 double dash minus k square psi 3 is equal to 0, where k square is equal to twice m epsilon by h cross square. Then your psi 1 is equal to a1 e to the power kx plus a2 e to the power minus kx, where x is smaller than a. And your psi 3 is equal to b1 e to the power kx minus b2 e to the power minus kx, where x is greater than a. And your a1, a2, b1, b2 are arbitrary constants. The condition psi tends to 0 as x tends to plus minus infinite demands that a2 is equal to 0 and b1 is equal to 0. Then writing a1 is equal to a and b2 is equal to b, we can obtain psi 1 is equal to a e to the power kx, where x is smaller than minus a, and psi 3 is equal to b e to the power minus kx, where x is greater than a. And now you have the region 2, where u is equal to minus u. Now the equation becomes psi 2 double dash is equal to twice m by h cross square u0 minus epsilon psi 2 is equal to 0, and your psi 2 double dash plus q square psi 2 is equal to 0, and your q square is equal to twice m by h cross square u0 minus epsilon. Since q square is positive, the general solution of the equation psi 2 is equal to c sin qx plus d cos qx, where c and d are arbitrary constants which can be evaluated by imposing the boundary conditions, that is psi is continuous across the boundary and d psi by dx is equal to psi dash is continuous across the boundary. So from these two boundary conditions, you can write psi dash at x is equal to minus a is psi 1 x at x is equal to minus a is equal to psi 2 x at x is equal to minus a. See here, in this region, in this discontinuity. Then we will discuss this discontinuity psi 2, psi 3. What happens here? Psi 2 at x is equal to a is equal to psi 3 at x is equal to a. Similarly, the first derivative psi 1 dash at x is equal to minus a is equal to psi 2 dash at x is equal to minus a, and psi 2 dash at x is equal to a is equal to psi 3 dash at x is equal to minus a, using these two boundary conditions 1 and 2. Now you can write a to the power minus k is equal to minus c sin qa plus d cos qa, and you can write the first derivative k a to the power minus k is equal to q cos qa plus d sin qa. Now, by differentiating both sides of the equation and dividing by equation a to the power minus k is equal to minus c sin qa plus d cos qa, you can get small k is equal to q c cos qa plus d sin qa by d cos qa minus c sin qa. Similarly, you can use other two equations and you will have b e to the power minus k plus c sin qa plus d cos qa, and by differentiating it, you have your minus bk e to the power minus k is equal to q c cos qa minus d sin qa. Now divide this, so you will get minus k is equal to q c cos qa minus d sin qa by C sin QA plus D cos QA. Now solve these two and you will get CD is equal to minus CD or CD is equal to 0. And this condition is satisfied if C is equal to 0 and D is not equal to 0. And if C is not equal to 0, D is equal to 0. So two classes of solutions are possible. One for C is equal to 0 and D is not equal to 0. And second for C is not equal to 0 and D is equal to 0. So the solutions are of even parity since psi 2 minus x is equal to psi 2x. It is symmetric. So you can have your k is equal to q tan qa and k is equal to qa tan qa, which is a transcendental equation. And solution belonging to second class where your c is not equal to 0 and d is equal to 0 yields psi 2 is equal to c sin qx and your k is equal to minus q cot qa or k is equal to minus qa cot qa because psi 2 minus x is equal to minus psi 2x. This is also a transcendental equation. So the energy levels can be found out, and these cannot hold simultaneously as they combine to give tan square qa is equal to minus 1 and tan qa is equal to I, which is a complex number. So this equation yields k is equal to iq, which implies that k square is negative. We should therefore give a positive energy capital E for a bound state which contradicts our original assumption that E is smaller than 0. And the energy eigenvalue can be found by solving these transcendental equations numerically or graphically. So that the graphical solution is very straightforward. So let us have the graphical solution. So this is the graph and how to get it. Your lambda is equal to QA and mu is equal to Ka, which are positive since Q, K and A are positive. And the transcendental equation takes the form mu is equal to minus lambda tan lambda for even solutions and mu is equal to minus lambda cot lambda is equal to lambda tan lambda plus pi by 2 for odd solutions. And your lambda square plus mu square is equal to k square plus q square multiplied by a square is equal to twice m by h cross square u0 square u0 a square is equal to k square. And your q square plus twice m by h cross square epsilon is equal to twice m by h cross square u0 and your twice m epsilon by h cross square is equal to k square. And your capital R is equal to twice m by h cross square u0 a square whole root over. And this represents a circle of radius capital R which is equal to root over of twice m u0 a square by h cross square. And the even solutions can be obtained by simultaneously solving equation 3.35 which is shown in the screen and 3.37 graphically. The odd solution can be obtained by simultaneously solving these two equations graphically. That is, your lambda square mu square is equal to k square and your mu is equal to lambda tan lambda plus pi by 2. It may be noted that the number of solutions depends on the radius of the circle capital R, which is in turn depends on u0 a square, that is strength of the potential times square of the range. And you can see u0 a square is equal to h cross square by twice m, your lambda square plus mu square is equal to 1 square, u0 a square is equal to 4h cross square by twice m, lambda square plus mu square is equal to 2 square, u0 a square is equal to 12h cross square by twice m, lambda square plus mu square is equal to 3.45 square. And your lambda and mu are restricted to positive values. Energy levels belonging to the first class can be found from the intersections in the first quadrant of the curve lambda tan lambda, which is nearly equal to lambda with the circles of known radii. And the energy levels that belongs to the second class solutions can be found from intersection in the first quadrant of the curve lambda tan lambda plus pi by 2, which is nearly equal to lambda with the circles of known radii, which is shown in the screen. For capital R smaller than pi by 2 or twice m by h cross square u0 a square whole root over smaller than pi by 2 or u0 square a square smaller than pi square h cross square by 8m, there is only one bound state. That is, for 0 smaller than u0 a square smaller than pi square h cross square by 8m, there is one energy level belonging to first class. for pi by 2 smaller than r smaller than pi, or pi square by 4 smaller than twice m u0 a square by h cross square smaller than pi square, or pi square h cross square by 8m smaller than u0 a square smaller than pi square h cross square twice m, there are two bound states, one belonging to the first class and other to the second class, as shown in the screen, figure 3.4. As u0 a square increases, more energy levels appear successively for the even class and odd class, and your bound state energy eigenvalues form a non-degenerate spectrum. This is expected for any one-dimensional bound state problem. Non-degenerate matlab it do not splits. And the number of bound states is finite and depends on the dimensionless parameter capital R. This in turn depends on u0 a square for a given mass. And the ground state is always an even state. The next bound states are alternatively odd and even. If 0 is smaller than capital R, smaller or equal to pi, there is one even parity bound state. If pi is smaller than capital R, smaller than 2 pi, there are two even parity bound states. In general, there are any even parity bound states if any minus 1 multiplied by pi smaller than R, smaller than any pi. And there are no odd parity bound states for 0 smaller than R, smaller or equal to pi by 2. There is one odd parity bound state if pi by 2 smaller than R, smaller or equal to 3 pi by 2. And in general, there are n0 odd parity bound states if n0 minus half pi smaller than R, smaller or equal to n0 plus half pi. Let us discuss the eigenfunctions next. And please see the figure, even solution and odd solutions. The eigenfunctions are similar to those of infinitely deep potential well, but they penetrate slightly into the classically forbidden region where they decay to zero exponentially, as shown in the screen. Then your infinitely deep well, we expect that in a limiting case of u0 tends to infinite, the results of the infinite deep well should be obtained as u0 tends to infinite, r tends to infinite, the allowed values of mu from the figure are mu n is equal to n pi by 2, where n is equal to 1, 2, 3, so on and so forth. And your energy eigenvalue En, the general formula, the expression is h cross square pi square by 8m a square multiplied by n square. Okay. Then there are some worked out examples. You can go through it. Then linear harmonic oscillator. And a linear harmonic oscillator or simple harmonic oscillator is a point particle attracted towards a fixed center by a force proportional to the displacement of the particle from the fixed center. And if the motion is so chosen along x-axis with the origin at the force center, then the force can be written as F vector is equal to minus kx vector, which is nothing but minus x cap du by dx, where k is the force constant and u is the potential energy function. So you can write u is equal to half kx square is equal to half m omega square x square, where k is equal to m omega square as shown in figure 3.6, and m is the mass of oscillating particle and omega is the angular frequency of the oscillation, and uk is u minus x, that is symmetric potential, and the potential energy function is a continuous function of x, and the plot is like this. Then the Hamiltonian of the oscillating particle is h cap is equal to p cap square by twice m plus half m omega square x cap square, and it has the property h cap minus x is equal to h cap plus x, that is symmetric. And the Hamiltonian of the oscillator is a symmetry function of x, and the time independent Schrodinger equation can be written as minus h cross square by twice m d square psi by dx square plus half m omega square x square psi is equal to e psi. That are the eigenvalue equation and its solution. The eigenvalue equation h cap psi is equal to e psi for the oscillator takes the form psi double dash is plus twice m by h cross square e minus half m omega square x square psi is equal to 0, and psi double dash plus twice m e by h cross square minus m omega square x square by h cross square psi is equal to 0. The eigenvalues and eigenfunctions of the oscillator can be obtained by solving this equation, and in order to achieve this, we introduce a dimensionless variable y is equal to m omega by h cross square root over multiplied by x. Now you can write d by dx, which is nothing but dy by dx into d by dy is equal to m omega by h cross root over d by dy. And your d square by dx square is equal to m omega h cross d square by dy square. Now substitute these two in equation 3.40 and you will get m omega by h cross psi double dash plus 2 e by h cross omega minus y square psi is equal to 0. And your m omega by h cross is not equal to 0, and the eigenvalue equation reduces to psi double dash plus lambda minus y square psi is equal to 0, where lambda is equal to 2 e by h cross omega. And before attempting for the complete solution of this equation, we analyze the behavior of the solution in the asymptotic region, that is y tends to infinite. Okay, and the asymptotic behavior is described here as y tends to infinite, y square is very greater than lambda, and for any finite value of e, the dimensionless variable lambda is negligible in comparison with y square, and the equation will reduce to psi infinite double dash minus y square psi infinite is equal to 0, whereas it is a function of y. So by solving this, you can arrive at the expression f double dash minus 2y f dash plus lambda minus 1 f is equal to 0. And you can solve it by power series method. So what is the power series solution of any differential equation? That is f, if f is taken as the summation s is equal to 0 to infinite as y to the power s, and you have the first derivative f dash, which is nothing but summation s is equal to 1 to infinite s y to the power s minus 1, and f double dash can be written as second derivative summation s is equal to 2 to infinite s into s minus 1 as y to the power s minus 2. Now you can solve it. You can know the Frobenius method or power series solution, how it is being solved by the your recursion relation and getting the values. You can have the solution, and En can be written as your n plus half h cross omega, and your E0 is half h cross omega, E1 is equal to 3 by 2 h cross omega, E2 is equal to 5 by 2 h cross omega, so on and so forth. And En minus 1 is equal to h cross omega. If you subtract your 3 by 2 h cross omega minus half h cross omega, it will be h cross omega. 5 by 2 h cross omega minus 3 by 2 h cross omega, it will be h cross omega. So there is two things. The energy eigenvalues are equispaced, they are same. En minus 1 is equal to h cross omega. So the energy spectrum is a discrete spectrum and it is equispaced. The difference is same, that is h cross omega. And second is, you see, E0 is not 0, it is half h cross omega. It is a non-zero value and it is called 0 point energy. At 0, the value is not 0, it has some value, so it is 0 point energy. And the eigenfunctions f double dash minus 2y f dash plus 2n f is equal to 0. This is Hermite differential equation, and its solution, you can know the Hermite polynomial, that is your Hn, that is minus 1 to the power n e to the power y square d to the power n by dy to the power n e to the power minus y square. Now it satisfies the recursion relation, and you have the wave function psi n is equal to alpha divided by 2n n factorial root over pi or to the power half your Hn, which is a function of alpha x e to the power minus alpha square x square by 2, and our h0 is y is equal to 0, h1 y is equal to 2y, h2y is equal to 4y square minus 2. You know, this is all about Hermite polynomial. And the eigen function corresponding to n is equal to 0, 1, 2, 3, so on and so forth, are psi 0 is equal to alpha by root over of pi to the power half e to the power minus alpha square x square by 2, and your psi 3 is equal to alpha by 48 root over pi to the power minus half 8 alpha cube x square minus 12 alpha x e to the power minus alpha square x square by 2. These are from Hermite polynomial. And the energy level diagram, which I was explaining you earlier, can be written like this. Your E0 is equal to half h cross omega, E1 is equal to 3 by 2 h cross omega, E2 is equal to 5 by 2 h cross omega, E3 is equal to 7 by 2 h cross omega, E4 is equal to 9 by 2 h cross omega. And you see, For n is equal to 0, the energy eigenvalue is half h cross omega. It is the lowest value of energy and is non-zero. This refers to ground state of the oscillator, and this minimum value of energy is called 0-point energy. And for n is equal to 1, 2, 3, so on and so forth, that are the excited states of the oscillator, the energy of the excited states are 3 by 2 h cross omega, 5 by 2 h cross omega, 7 by 2 h cross omega, so on and so forth. And the spacing between two adjacent levels is del En is equal to En plus 1 minus En is equal to h cross omega, which is independent of n. So the energy levels of harmonic oscillator are equispaced, as I have told you earlier. And your del En by En is equal to 2 by 2n plus 1 is equal to 1 by n plus half. And if n is very, very large, then del En by En is nearly equal to 1 by n, because n is very, very large as half, and you can write it as 1 by n. And when n tends to infinity, 0, and I am I audible? 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 Am I audible, or shall I disconnect and am I audible?
Yes, sir.
Thank you. So the ground state wave function psi 0 has no node. You can see here. It is a Gaussian function of x, and the first excited state psi 1 has one node. The second excited state psi 2 has two nodes. So in general, wave function of n state has n nodes, and the energy levels wave function psi and their probability density psi square for the first four states are presented in the figure. And the intersection of probability curve with the potential curve u gives the classical limits of oscillation. So there is finite probability of observing the particle outside the classical limits of the oscillation, and the probability density of the harmonic oscillator in n is equal to 11 state is shown also in the screen. Here, it is here. So there are some examples. Compute del x by del p for nth stationary state of harmonic oscillator, so that ground state is the minimum uncertainty product, so that the expectation value of potential and kinetic energy are equal in the stationary state of harmonic oscillator. Your 0-point energy of harmonic oscillator is a consequence of uncertainty principle. You can determine the probability distribution for various values of momentum of harmonic oscillator. One-dimensional oscillator having mass 10 to the power minus 20 kg oscillates under force constant k is equal to 10 to the power minus 4 Newton meter to the power minus 1. You can evaluate 0-point energy, calculate the classical amplitude for which oscillation have its energy, and the energy for the second excited state you can calculate, and it is shown in the screen. Then quantum theory of hydrogen-like atom. Angular momentum operator in Cartesian coordinate system. So you know L vector is equal to R cross P vector, and your L can be written as I cap, J cap, K cap, X, Y, Z, P X, P Y, P Z as shown in the screen, and Lx is equal to Y P Z minus Z P Y, Ly is equal to Z P X plus X P Z, Lz is equal to X P Y minus Y P X, and your Lx cap is equal to Y cap, P Z cap minus Z cap, Py cap, and your Ly cap is equal to Z cap, Px cap minus X cap, Pz cap, Lz cap is equal to X cap, Py cap minus Y cap, Px cap. And by substituting these values of the position operator and the linear momentum operator in the equation, you get the corresponding angular momentum operator, that is Lx cap is equal to Y minus IH cross del by del Z minus Z minus IH cross del by del Y. Similarly, you have Lx cap can be written as minus IH cross Y del by del Z minus Z del by del Y. Similarly, Ly cap can be written as IH cross Z del by del X minus X del by del Z, and Lz cap is equal to minus IH cross X del by del Y minus Y del by del X. So the angular momentum operator in Cartesian coordinates can be written as your X is equal to R sin theta cos phi, Y is equal to R sin theta sin phi, Z is equal to R cos theta. And the inverse relations are R is equal to root over of X square plus Y square plus Z square, and your cos theta is equal to Z minus Z by R, and tan phi is equal to Y by X. And now you can have your del by del X, del by del Y, del by del Z in terms of R theta and phi, and you have to consider the function U, which is a function of R theta and phi in spherical polar coordinate system. And your del U by del X can be written as del U by del R multiplied by del R by del X plus del U by del theta by del X, del U by del phi by del X, your chain rule. So your 2R del R by del X is equal to 2X, and your del R by del X is equal to sin theta cos phi. Now differentiate it with respect to X, and you will have sec square phi into del phi by del X is equal to minus Y by X cross square, which is equal to minus R sin theta sin phi by R sin theta cos phi square, and your del phi by del X is equal to minus sin phi by R sin theta. Okay. Now differentiate it with respect to X, and you will get minus sin theta del theta by del X is equal to cos theta cos phi by R, and your del U by del X is equal to sin theta cos phi del by del R plus cos theta cos phi R del by del theta minus sin phi R by R sin theta del by del phi multiplied by U, and your del by del X is equal to sin theta cos phi del by del R cos theta cos phi by R del by del theta minus sin phi by R sin theta del by del phi. So the chain rule for partial differentiation, that with respect to Y and Z, will give del by del Y is equal to sin theta sin phi del by del R plus cos theta sin phi by R del by del theta plus cos phi by R sin theta del by del phi. So your del by del Z is equal to cos theta del by del R minus sin theta by R del by del theta, and your component Lx of orbital angular momentum in terms of spherical polar coordinate system can be written as Lx cap is equal to minus IH cross Y del by del Z minus Z del by del Y. Similarly, you will have Lx cap will be minus I h cross minus sin square theta sin phi del by del theta minus cos square theta sin phi del by del theta minus cos theta cos phi sin by sin theta del by del phi, which is nothing but your I h cross sin phi del by del theta plus cos theta cos phi sin by sin theta del by del phi. Similarly, you can have your Ly and Lz. So Ly can be written as I minus IH cross cos phi del by del theta minus cos theta sin phi by sin theta del by del phi, and Lz can be written as minus IH cross x del by del y minus y del by del x, which is nothing but minus IH cross del by del phi, and the derivation is shown in the screen. And square of the orbital angular momentum we will calculate, it will be nothing but L cap square is equal to Lx cap square plus Ly cap square plus Lz cap square, and we will have your minus h cross square 1 by sin theta del by del theta sin theta del by del theta plus 1 by sin square theta del square by del phi square. Now you can write Schrodinger equation for spherical symmetric potential. For that, the potential energy of the particle moving under a central spherically symmetric field of force depends only upon the distance from the center of force, that is potential energy in such cases, has form U, which is a function of r being the distance between the particle and the center of force, that is the origin. And the Schrodinger equation in such a system can be written as del square psi plus twice m by h cross square E minus U psi is equal to 0. And in such cases, it is appropriate to write the Schrodinger equation in spherical polar coordinate system, that is in terms of r, theta, and phi. Since the potential energy U, which is a function of r, is independent of the angular variable, that is theta and phi. So let P in the figure, you can see P be the point in the space such that its Cartesian coordinates are x, y, x, y, z. Then the spherical polar coordinates of the point P specified by r, theta, phi, where r is equal to P is the radius of the sphere on which point P lies. Theta is the co-latitude, that is the angle between OP and Z axis, and phi is the longitudinal or azimuthal angle, that is the angle included between xy plane and the plane OPZ. So you can write the transformation between Cartesian coordinates and spherical coordinates are given by x is equal to r sine theta cos phi, y is equal to r sine theta cos sine phi, and z is equal to r cos theta. And you can have your x square plus y square plus z square is equal to r square, and your r is equal to root over of x square plus y square plus z square, and tan phi is equal to y by x, and tan theta is equal to root over of x square plus y square by z. Now by using these equations, am I audible? Am I audible? Am I audible? Am I audible? Am I audible?
Yes, sir.
Yes, sir.
Okay. So this is all about hydrogen atom. And the complete solution of the hydrogen atom, hydrogen like atom problem, can be derived from the Schrodinger wave equation for spherically symmetric potential in spherical polar coordinate systems, which is given by 1 by r square del by del r square del psi by del r plus 1 by r square sine theta del by del theta sine theta del psi by del theta plus 1 by r square sine square theta del square psi by del phi square plus twice mu divided by h cross square E minus u psi is equal to 0, where mu is the reduced mass, E is the energy of the particle, and u, the potential in CJ system, is minus E square by r, and it is for electron proton system of hydrogen atom. To solve the equation, you have to express the eigenfunction psi as a product of the functions r, theta and phi, which are the function of small r, small theta and small phi respectively, and you can write your psi is equal to r, theta and phi. So you can solve it by separation of variable, which I have, which is there in the mathematical physics course of your MPH-01, I think. And you have the solution. You can see here by separation of variable, you can have the solution: theta equation, phi equation, r equation, and the solution is your first we have the radial solution. 1 by r square del by del r square del r by del small r minus l into l plus 1 by r square r plus 2 mu by h cross square E minus u multiplied by r is equal to 0. And if you put u is equal to minus z e square by r, where z is the z is equal to 1 for hydrogen like atom, and E is the charge of the electron, and r is the radius. So you have the solution by solving it. Your r, which is a function of rho, is equal to e to the power rho by 2, and r, which is a function of rho, can also be e to the power minus rho by 2, as rho vary from 0 to infinite. Formula of these solutions will increase as rho increases, and so it will lead to an unacceptable wave function. On the other hand, the second solution decreases as 0 as rho, hence r increases to infinite. So the second solution is satisfactory, where r is equal to e to the minus rho by 2. Now from the recursion formula, you have the asymptotic solution, and by solving it, you will have the hydrogen like atom problem solution. En is equal to mu z square e to the power 4 to h cross square n square, and the radial wave function can be written as RNL is equal to root over of 2z by n a0 q n minus l minus 1 by 2n n plus l factorial q e to the power minus zr by n a0 2zr divided by n a0 to the power l subscript n plus l superscript 2l plus 1 2zr by n a0. And the first radial functions, that is r10, r20, r221, are shown in the screen. Then the complete wave function is the radial and theta and phi part, and this is shown in the screen. And for n is equal to 1, L is equal to, for n, L, m values, n1, L0, m0, you have the 1s state, n2, L0, m0, 2s state, n2, L1, m0, 2p state, n2, L1, m1, 2p state. The eigenfunction psi 1, psi of 100, psi 200, psi 210, psi 211 can be written as shown in the screen. and you can have your psi NLM value I have shown in the screen. And then the quantum number, we have come across three quantum numbers, N, L, and M. We specify the energy eigenfunctions of the electron in a hydrogen-like atom, and the quantum number N and the energy eigenvalue are given by the formula En is equal to minus mu e to the power 4 by 8 epsilon 0 square h square z square by n square, where En are completely specified by small n, and this n is called principal quantum number. It can have the values 1, 2, 3, 4, 5, 6, so on and so forth. And your E1 is equal to minus mu e to the power 4 8 E0 square h square, E2 is equal to E1 by 4, E3 is equal to E1 by 9, so on and so forth. So the energy is quantized, and the quantization of electron energy in hydrogen-like atom is therefore described by principal quantum number, that is n. Then your quantum number L, this is orbital angular momentum quantum number, and it is directly related to the magnitude of the L vector of the electron through the equation, and modulus of L vector is equal to L into L plus 1 to the power half h cross, and the spherical harmonics are eigenfunctions of L vector cap with the square with the eigenvalues L into L plus 1 h cross square, and L is permitted to take integral values from 0 to n minus 1. And this is, orbital angular momentum quantum number, and the integral values of L imply that angular momentum of electron is quantized. And the state with L is equal to 0, 1, 2, 3, 4, 5 are labeled for historical regions as S, P, D, F, G, H respectively states, and the atomic states in each atom are designated by the combination of the values of N and vector corresponding to the given L value. So if n is equal to 1, L can be 0, 1, 2. If n is equal to 1, L is equal to 1 minus 1 is equal to 0, and it corresponds to 1s state. If n is equal to 2, then L can be 0 or 1. N minus 1 is equal to 1. So from 0 to 1, it is 0, 1. And L is equal to 0 corresponds to 2s state, and L is equal to 1 corresponds to 2p state. Similarly, if n is equal to 3, for L is equal to 0, it is 3s state, L is equal to 1, 3p state, and L is equal to 2, 3d state. If n is equal to 4 and L is equal to 0 corresponds to 4 state, L is equal to 1 corresponds to 4p state, L is equal to 2 corresponds to 4d states, and L is equal to 3 corresponds to 4f states. And if n is equal to 5, then L is equal to 0 corresponds to 5p state, L is equal to 1 corresponds to 5p states, L is equal to 2 corresponds to 5d state, and L is equal to 3 corresponds to 5f state, and L is equal to 4 corresponds to 5g states. For n is equal to 5, n minus 1 is equal to 4. So you can have maximum L value 4. Then another quantum number is M, which is magnetic quantum number, and the angular part of the wave function is characterized by the quantum number M, which is the orbital magnetic quantum number, sometimes we call it. It specifies the direction of angular momentum vector L vector in the field direction, and the eigenvalues of Lz cap are mh cross, where M takes on 2L plus 1 values, that is minus L plus 1, so on so forth, 0, 1, 2, so on so forth, L. So the number of possible orientations of L vector in a magnetic field is 2L plus 1. So the space quantization of orbital angular momentum vector is described by the orbital magnetic quantum number small m. And the degree of degeneracy of the energy level is a number of eigenfunctions corresponding to a particular energy level. And the energy and the eigenfunctions of hydrogen-like atom are specified by three quantum numbers N, L, and M. And for a given N value, you have L is equal to 0, 1, 2, so on and so forth, N minus 1. And for a given L value, M takes the value 2L plus 1 from minus L to plus L, and in between 0. Hence, for the nth energy level, the degree of degeneracy is Gn is equal to summation L is equal to 0 to n minus 1 to L plus 1, which is nothing but 2 into n minus 1 into n by 2 plus n. And Gn can be written as n square. So the nth level is n square fold degenerate, that is n square eigenfunctions corresponds to a given En. And energy level diagram, you can have the energy level nth state of hydrogen atom, that is Z is equal to 1, is given by En is equal to minus mu e to the power 4 by 8 epsilon 0 square s cross square whole multiplied by 1 by n square, that is nothing but minus 13.6 by n square electron volt, where n is equal to 1, 2, 3, so on and so forth. and the highest value of En is 0, which corresponds to n tends to infinite, and the lowest value of energy corresponds to n is equal to 1, and it is given by U1 is equal to minus 13.6 electron volt, and it is called the ground state energy. And the states with n is equal to 2, 3, 4, so on and so forth are the first, second, third excited states respectively, and the value E2 minus E1 is 10.2 eV, E3 minus E2 is 1.86 eV, E4 minus E3 is equal to 0.66 eV, and it is not equispaced, you can see. And your Gn is equal to n square is equal to n is equal to 1 level is the non-degenerate, and the state is 1s. And n is equal to 2 level is 4-fold degenerate, n is equal to 3 is 9-fold degenerate, and so on and so forth. And this can be shown as shown in the screen, E1, E2, E3, E4. So in a hydrogen-like atom, it is not equispaced, energy levels are not equispaced, but in harmonic oscillator, the energy levels are equispaced. So there are some worked out examples. You can go through it, find the expectation value of R in the ground state of hydrogen atom, and you can calculate it. It is 3 by 2 A0. Find the expectation value of potential energy of electron in the ground state of hydrogen atom. It is minus E square by 4 pi epsilon 0 A0, and the solution is there in the screen. And find the most probable radius of electron of a hydrogen atom in 1s state. It is A0, and the solution is shown in the screen. Find the most probable radius of the electron of a hydrogen atom in the 2p state, and it is 4a0, and the solution is shown in the screen. So this is the basic understanding by which you can have different solutions of your hydrogen-like solutions of quantum mechanics in different real-life situations. And you can see the free particle where there is no potential energy or U is equal to 0, and I have described how psi can be written as A to the power minus EIX, A to the power IKX plus B to the power minus IKX, one in a positive x direction, another is minus x direction, and particle in a box. There are two regions. In one regions, here this is a potential V, and in 1 and 3 region there is no potential, and here can discuss it. Then eigenvalues and eigenfunction, these are not equispaced, and first three eigenfunctions are particularly in a box, and the nodes then thereof. Then time dependent wave function, their probability density are shown in the screen. Then your quantum dot, one dimensional particle, zero dimensional particle, quantum dot, and its application is enormous. Then energy of particle where the potential is greater, reflection and transformation coefficient. Potential barrier, 1, 2, 3, three regions. A part is transmitted, a part is reflected, and there is a damping in region 2. Reflection and transmission coefficients, and that is 1. One is a finite potential well, 3 regions. In the Schrodinger equation, the graphical solution I have explained you. This is a graphical solution. Then harmonic oscillator problem, stationary state Schrodinger equation, its solution, power series solution I have explained you in this class. Then your boundary conditions and eigenfunction, how to solve it, and the energy, equispaced energy levels, and the 0-point energy. And these are the eigenfunctions graphically shown here. Then energy eigenvalues, then symmetric, anti-symmetric. Then your hydrogen-like atom. For that, you use spherically symmetric potential, three-dimensional equation. Then in spherical polar coordination, which I have explained you today, and it's a solution for hydrogen-like atom. Hydrogen-like atom problem. Radial equation solution, theta solution, phi solution using power series or Frobenius method, which I have explained you today. And the wave functions psi 11, psi 21, psi 30, psi 100, psi 200, psi 300. So I have explained you today. Then degeneracy, radial probability density, spectra of the hydrogen atom, quantum numbers. I have explained you today four quantum n, l, m, and spin quantum number is another plus minus half. So this is unit 2. And in unit 1, yesterday we are discussing all these things. Then observables and operators. The operator formalism is one of the very important formalism by which you can also solve quantum mechanical problems. Energy operator, Hamiltonian operator. So these are also very much useful. These can be solved by using matrix algebra. Parity operator, even and odd parity can be checked from that. Then properties of operator. It commutates or do not commutate. Commutator algebra. A cap, B cap does not necessarily B cap, A cap. It can have also minus B cap, A cap. Similarly, other commutator properties, linear and anti-linear operators, expectation value, or the the expectation value is integration minus infinite to infinite x p, which is a function of x comma t dx, and this is the expression, the average value of the expectation value. Then Hermitian operator for a physical observable. This is very much important. In the first class, I have explained the eigenfunctions and eigenvalues. Eigenfunctions, when an operator is operated upon an eigenfunction, it will give eigenvalue multiplied by that eigenfunction. So eigenvalue is nothing but the value of that particle. Suppose momentum operator operated upon psi will give you momentum eigenvalue, energy operator operated upon psi will give you energy eigenvalue, so on and so forth. Then commutating and non-commutating operators, orthonormal eigenfunctions, Onfest theorem. This is very much important. And the postulates of quantum mechanics, the state of a quantum mechanical system is completely specified by a function psi that depends on the spatial coordinates and time. This function is called the wave function of the system, and all possible information about the system can be derived from the wave function. Every physical observable of the system is associated with the Hermitian operator which acts on the wave function. The only possible results of the measurement of the observable associated with an operator d cap is one of the eigenvalues of d cap, which can be derived from the eigenvalue equation d cap psi is equal to d psi. And if a system is in a state described by a normalized wave function, then the average measured value of the observable corresponding to the operator d cap is given by your psi star d cap psi d tau volume integral. The wave function of the system evolves in time according to the time dependent Schrodinger equation, that is I h cross del psi by del t is equal to minus h cross square by twice m del square psi by del x square plus v multiplied by psi. Okay. So your linearity and superposition principle, your operator formalism, eigenvalues and eigenfunctions, all about linear operators, null operators, algebra, equality, addition, product, commutation of two linear operators, commutation relation between position coordinates and momentum operators in coordinate space and in momentum space, how you can write those things. And commutator algebra and its proof is shown in the screen. In Hermitian operator in quantum mechanics, a physical quantity Q is represented by a linear operator Q cap. The expectation value of Q in the state psi is given by expectation value of Q, which is shown as a bracket in the as shown in the screen, is equal to integration psi star Q cap psi dqr, where psi is a normalized wave function and the expectation value of Q in the state psi is a real quantity. So you can have your Q is equal to Q star, but expectation value of Q star is equal to integration psi star Q cap psi dqr whole star. So this is nothing but integration Q cap psi star psi dqr. And this implies that your integration psi star Q cap psi dqr is equal to integration Q psi star psi dqr, and operator satisfying this equation is called Hermitian operator, and any operator represents a physical observable is must be a Hermitian. Then your expectation value and the formula how to evaluate it. In general, formula for expectation value is shown in the screen. Expectation value position, that is integration minus infinite to infinite psi star x psi dx. Expectation value momentum I h cross integration minus infinite to infinite psi star del psi dqr. And for one dimension minus I h cross integration minus infinite to infinite psi star del by del x psi dx. Expectation value of energy, that is I h cross integration minus infinite to infinite psi star del by del t psi dx. And there are some worked out example you can. Then expansion of an arbitrary wave function as a linear combination of energy eigenfunctions. The energy eigenvalue En are always real. The energy eigenfunction psi n form a complete orthonormal set, and they are normalized as well as orthogonal. These eigenfunctions define the so-called Hilbert space named after the famous mathematician David Hilbert. And any arbitrary wave function that is continuous, single-valued, finite, and describes a possible quantum state can be expressed as a linear combination of eigenfunctions psi n of the Hamiltonian operator H cap, as psi is equal to summation n Cn psi n, and this is called the expansion coefficient Cn, and you can evaluate Cn as shown in the screen. Integration psi n star psi dqr, and the physical significance of Cn, it is shown here. then complete relation, energy of arbitrary quantum states, then closure relation, general solution of time-dependent Schrodinger equation in terms of linear combination of stationary states, phase velocity, group velocity for non-relativistic one, for relativistic one, dependence of phase velocity upon group velocity, u is equal to c multiplied by 1 plus m0 square c square lambda square by s square to the power half. For zero mass rest mass, your u is equal to c. Then superposition of two waves, group velocity and phase velocity concept, their derivation, relation between phase velocity and group velocity, dg is equal to u minus lambda du by d lambda. Wave packet, which I have told you in the first class, it represents a particle and it can be constructed by superposing a large number of waves so chosen that they interfere constructively in a localized region of space and interfere destructively elsewhere. And the localization constant in time can represent a particle. And how to construct a wave packet, it is shown in the screen. Then group velocity of photon from the expression Gaussian wave packet, psi is equal to integration minus infinite to infinite b, which is a function of k e to the power I kx minus omega t dk. And width of Gaussian packet in x space, in k space, del x is equal to 2 root over of 2 alpha, and del k is equal to 2 root over of 1 by 2 alpha, and the derivation is shown here. Momentum space wave function, physical significance of phi, expectation value of p, uncertainty principle. The uncertainty principle states that it is impossible to measure simultaneously with absolute precision two canonically conjugate variables. So if P and Q are two canonically conjugate variables, the product of uncertainties in Q and P is greater than or of the order of H cross. So you can write del Q dot del P is greater or equal to H cross, where H cross is equal to H by 2 pi, where H is Planck's constant. And your del P and del Q are uncertainties in measuring P and Q respectively. So del x plus del px is greater or equal to h cross, del y plus del py is greater or equal to h cross, del z plus del pz is greater or equal to h cross. So position and momentum are canonical conjugate variables and their product is greater or equal to h cross. Similarly, position, momentum, uncertainty relation, you have azimuthal angle and Lz, orbital angular momentum. These are also canonical conjugate variables. So you have del phi, del Lz is greater or equal to T and is greater or equal to H cross. This is also an uncertainty relation. Similarly, del T, del E is greater or equal to H cross, time and energy uncertainty relation. So in general, del Q dot del P is greater or equal to H cross by 2. And the minimum value of the uncertainty product is H cross by 2. And if one measure the x coordinate of the particle with 100% accuracy, then del px tends to infinite. That is, the x component of the linear momentum of the particle is infinitely uncertain. On the other hand, if one measures the x component of linear momentum with 100% accuracy, that is del px is equal to 0, then del x tends to infinite. That is, the position of the particle measurement becomes infinitely uncertain. So, simultaneous measurement of position and momentum with 100% accuracy is not possible, and the precise relation between del x and del px depends on how one defines the limits of uncertainty in a particular case. It is observed that the uncertainty product is of the order of Planck's constant, that is h. So there are some worked out examples, you can go through it. Then general discussion of bounds in an arbitrary potential, which I have discussed you earlier today. These are the
Sir, I'm in note side.
Am I audible?
Yes, sir.
Okay. So in the third block, you have the Hilbert space, which I have discussed to you today, and the Dirac notation, which is also very much important, and the linear operators in Hilbert space, eigenvalues and eigenvectors, infinite dimensional Hilbert space. So these will be discussed in the next class. Okay. Anything else?
सर हमें नोट चाहिए.
हाँ, तो कोर्स मटेरियल से करो, अगर जरूरत होगा तो नोट देंगे और क्या. ठीक है.
ठीक है.
आपका मटेरियल में भी सारी चीज है, और मैंने जो उसमें जरूरी है उसको मैंने आपको एक्सप्लेन कर रहा हूँ. ठीक है.
ओके सर.
इफ यू वांट द नोट आइदर, देन देखेंगे, उसको भी देंगे, क्या है. ठीक है.
ठीक है.
थैंक यू. आप पहले कोई जो ये ब्लॉक 1 और ब्लॉक 2 दोनों आपको कंप्लीटली उसको देखो. आपका कोर्स मटेरियल, उसमें जो क्वेश्चंस है, टर्मिनल क्वेश्चंस, उसका सॉल्यूशन आंसर, उसको प्रैक्टिस करो. अगर जरूरी होगा तो हम भी नोट देंगे, क्या है. ठीक है.
ओके.
थैंक यू. आपको समझ में कुछ आ रहा है या कुछ समझ में नहीं आ रहा है? बिल्कुल.
सर थोड़ा थोड़ा आ रहे हैं, तो हमें when we go through the books and
वेरी ह्यूज कोर्स एंड ओनली 8 hours. सो तो थोड़ा थोड़ा आएगा, फिर आप जब पढ़ेंगे पूरा पूरा आ जाएगा.
after go through the books then we can understand.
ओके. थैंक यू.
Okay, sir.
थैंक यू.